In lesson 1, we introduced the concept of limit and the concept of a rate of change. And in this lesson, we're going to associate those to the definition of the derivative. Let's start with a function f of x as depicted in this diagram. My function f of x contains a point p that we're going to define it as having coordinates x and y. This point P is going to be fixed. We're not going to change it. But I will introduce one second point that I'm going to call Q. And this point Q is going to have coordinates x1, y1. So let's call it Q1 because we're going to use several ones. What I want to see is what happens to the line that joins P and Q as Q gets closer to P. So I want to show the line that joins P and Q. If I change the point Q, obviously the line is going to change. So let's choose a different point that is going to be closer to P. So right here we're going to have Q2 that has coordinates x2, y2. Then the line that goes through P and Q will have changed and is now this line right here. We can continue to choose points that are closer to the value xy that we have. So I'm going to choose one more closer. Let's call this one Q3. It will have coordinates Q3, y3. And the line that will join P and Q3, let's choose one more, a little bit closer to P. Let's say this point right here with coordinates x4, y4. And the line that will join P and Q is going to be this one. Now I can continue to choose points that are closer and closer to P, but I want to make an observation first. The first thing that I want to notice is that obviously the slope of the line is changing because I'm changing the coordinates of the point Q. Generally, I'm going to calculate the slope of this blue line as the difference between the coordinates of P and Q. So that's going to be y minus yn over x minus xn, where yn and xn are representing all the possible values for the coordinates of the point Q, and x and y is this point P. One more thing that I can observe is that in the beginning, P and Q were very different. So the line is cutting the graph in two different points. Obviously, one of the points is P and the other point is Q. But notice that as P and Q get closer, that line kind of seems to start changing. It is still cutting in two different points, P and Q. But when I get to the point where Q is so close to P that it will be indistinguishable, then the graph of the line is only going to touch one point of the curve f of x. What does that mean? That means that in the limit, when Q gets closer to P, the line is no longer a second line touching in two different points, but it will be a tangent line at the point P. So if we think about what we were discussing before with the limits and the rates of change, what's the equivalent here? The slope of the line as Q gets closer to P starts giving different information. While Q is far away from P, the slope of the line given by y minus yn over x minus xn is representing a rate of change of the function, but is measured over an interval, just like you would the average speed of a car. However, When we bring that point Q closer to that point P, P and Q become indistinguishable, and the slope of the line is representing the rate of change of the function at that specific point P. So it is the equivalent of the instantaneous speed of a car. And the slope is given by the limit when xn, which is the x-coordinate of u, approaches x of y minus yn over x minus xn. This would be the representation of the instantaneous rate of change. So what do we learn? We learned that the instantaneous rate of change at a point P is given by the slope of the tangent line at the point P. We also can gather from this that the slope of the tangent line is going to carry important information about growth for the function. When the slope of the tangent line is positive, the function will be increasing. When the slope of the tangent line is negative, the function will be decreasing. And when the slope is 0, the function will be constant or will be at a turning point of some sort. Can you match the diagrams marked 1, 2, and 3 with one of these three cases A, B, and C? Because of all the information that the slope of the tangent line carries, it is one of the most important features that we can study in a graph, and we have given it a special name. We call the slope of the tangent line the derivative of the function at the point P. So at point P, if I wanted to find how is the function changing, I need to look at the derivative of the function. If I want to find a line that is tangent to my function, I need to first find the derivative of the function in order to find the slope of the tangent line. The derivative of the function f of x will be very important to us to learn about the function's behavior. Growth, as in, is it increasing, is it decreasing? Does it have turning points, maximum and minimum values? Does it have inflection point, changes of concavity? Or does the function simply not change and remain constant? In the next part, we are going to introduce you to the way to calculate derivatives for polynomial functions. And we're going to look into some applications and word problems.